All right, let's jump right in. We're talking about the incredible world of composite materials. You know, the super light, super strong stuff that's in everything from fighter jets to high-end race cars. But these materials have a hidden and sometimes pretty catastrophic weakness. And that question right there, that's the central paradox we're digging into. How can something so incredibly strong also be, well, so fragile? It's a mystery that has been a real headache for engineers for decades, but some brand new research is finally starting to crack the code, and we're going to break down exactly how. Okay, so first, why even bother with these materials? Well, it all comes down to their incredible strength to weight ratio. I mean, just look at this comparison. When it comes to being strong and light, fiber composites just blow traditional metals like steel and even aluminum out of the water. It's not even a competition. That's why they're so critical for building things that need to be light and fuel efficient. But, and this is a huge but, here's the catch. If you pull on a composite, its tensile strength is amazing. But if you push on it, if you compress it, its strength can just plummet, sometimes to only 60% of its pulling power. This unpredictable weakness has been a massive roadblock, really limiting how far we can push the designs of these materials. So, here's our game plan. We're going to start with this paradox. Then we'll do a little detective work on the anatomy of how these things actually fail. We'll look at a mind-blowing breakthrough in watching this failure happen live, and then cover a revolutionary new way to simulate it. And finally, we'll pull it all together to see what this means for the future of new materials. So let's start with the composite paradox. The real mystery here is figuring out why there's this dramatic drop in strength when you squish it, and maybe more importantly, how to predict when and where that failure is going to happen. To solve this mystery, scientists basically had to become detectives. They needed a way to peer deep inside a composite material at the exact moment it was being crushed to see the anatomy of its failure, step by step. And the number one culprit they were hunting for is something called a kink band. So picture thousands of microscopic fibers all lined up. When you put them under compression, they can suddenly buckle all at once in a tiny localized band, like a sharp bend or a kink. And this whole thing happens in a flash, leading to total catastrophic failure. This is the smoking gun. Now, the problem is, saying it happens in a flash is a bit of an understatement. To actually catch it in the act, a team led by Wang used this incredible setup at the Swiss light source. They basically put a tiny sample of a composite in a press, and while crushing it, they blasted it with super powerful, high-speed X-rays. Think of it like a medical CT scan, but on steroids, running fast enough to create a 3D movie of the material breaking apart. This gave them the first ever 3D, real-time video of individual fibers at the very moment before they snapped. And what they saw? Well, it changed everything. Because in those final fractions of a second, they found a hidden clue, a tiny, almost invisible warning sign that pops up just before the whole thing gives way. And the really crucial discovery was when all this action happens. Take a look at this timeline. For almost the entire time it's under load, I'm talking up to nearly 98% of its breaking point, everything looks fine. Then all the drama happens in that last tiny fraction of a percent. First, the fibers start to tilt just a little. Then the load barely increases, and that tilt becomes a sharp knee. Then a clear microbuckle band shows up just moments before total collapse. This isn't a gradual thing. It's a sudden, terrifying cascade. This shows you just how subtle that warning sign really is. The precursor, this microbuckle, is incredibly small, with the fibers just tilting at a shallow 8 degrees. But the final, catastrophic kink band, it's more than twice as wide, with a much steeper, much more violent angle. Finding this tiny precursor was like finding a faint tremor just seconds before a massive earthquake hits. The other huge insight was that in the real world, these fibers are not perfectly straight. Nope, they have all these tiny random waves and wiggles from when they were made. And as the researchers point out, this messy reality is way more complex than the perfect, idealized shapes that old computer models used. This right here is why predicting failure has been so ridiculously hard. The old models were just too neat and tidy for the real messy world. Okay, so now scientists could finally see the problem in stunning detail. But seeing it is one thing. Predicting it, that's the holy grail. And that brings us to the next part of our story, the simulation breakthrough. So the challenge was, our tools for simulating this stuff just weren't up to the job. The traditional models, which have to calculate every little bit of every single fiber and all the stuff around it, are painfully slow. Trying to simulate the messy, wavy reality of thousands of these fibers was pretty much computationally impossible.
And when I say painfully slow, I am not kidding. Get this. A study that Bykos and his team cited found that simulating a tiny little chunk of composite with just 40 fibers took almost 2 weeks of computer time. And to actually design something useful, you need to simulate thousands of fibers. You can do the math, it would take years. This was the bottleneck holding everything back.
So to break through that bottleneck, you don't just need a small improvement, you need a massive leap forward. And that is exactly what another team delivered, a brand new method that cut simulation time by over 99.9%. No, that is not a typo. A 2-week simulation suddenly became a matter of minutes. This is a complete game changer. I mean, this chart really says it all. What used to take weeks of a supercomputer just grinding away can now be done in the time it takes you to make a cup of coffee. This just throws the doors wide open to testing thousands of different material designs virtually, super quickly and cheaply. So how on earth did they do it? Well, the genius of their Shelby method is how elegantly it simplifies the problem. Instead of modeling each fiber as a complex 3D shape, they model its basic structure as a simple 1D beam. And the stuff holding the fibers together, the matrix, is modeled as simple 2D shells. By just capturing the essential physics of how these parts push and pull on each other without all the extra computational baggage, they got this incredible speed up while still being over 94% accurate. It's brilliant. And this brings us to the really exciting part, how these two separate breakthroughs, one in seeing the problem and one in simulating it, come together to create a powerful new future for designing materials. Think of the first discovery from Wang's team as giving us the blueprint. For the very first time, we have these incredibly detailed, accurate 3D maps of what real fibers actually look like and how they behave under stress, including all their messy, real-world imperfections.
But a blueprint isn't very useful if you don't have an engine to build with, right? And that's exactly what Bykos' team built. They created the engine, a simulation tool that's powerful and fast enough to actually use those complex, messy blueprints to predict the material's breaking point with amazing speed and accuracy.
So why does all this matter? Well, because with this blueprint and engine finally working together, engineers can design composites that aren't just stronger, but are way safer and more reliable. They can test endless variations on a computer to find the perfect recipe, which will lead to more fuel-efficient airplanes, longer-lasting wind turbine blades, and even next-generation spacecraft that we just couldn't design with any confidence before. You know, this combination of seeing and simulating has basically just erased a barrier in material science that's been there for decades. It finally closes the loop from observation to prediction. And it leaves us with one really fascinating final question. Now that we have the tools to understand and predict the breaking points so precisely, what new class of impossible materials are we going to be able to create next?